NCERT for commutative rings. So now what I'm going to do is, again, I'm going to go back to Atiyah McDonald, chapter 1. So we're going to do some things from there about ideals, radicals, prime ideals, maximal ideals, things like this. All of this we will try to see in examples of rings. So recall the main examples of rings that we have are the following. So Z is one, the ring of integers, Kx, polynomial ring in one variable over a field. So these are two very important examples. Other than this, you could consider Kxy, a polynomial ring in two variables over a field K. And in addition, we considered the ring Z adjoined I and Z adjoined omega. So these were the 5 examples of rings I gave, in addition to fields plus fields. Fields plus all of this. Okay, so these are all examples of rings, but these rings are all in some sense very nice in various ways. Particularly the rings Z and Kx are extremely well behaved rings. Of course, fields are the best kind of rings that you want, but we would also like to have examples of rings which are not as well behaved. So the way to get examples of rings which are not as nice is to take quotients of these rings by ideals. So if I is any ideal in R, in a ring R, if I contained in R is an ideal, then we may form the quotient ring R mod I. And this construction is important because it's going to give you lots of examples of rings. Right? You can take any ideal in any of these rings and take the quotient and you'll get a new ring. And that gives you lots of examples of rings. So we may form the quotient ring R mod I. So what is this? This is the cosets This consists of all cosets of R, set of all R plus I, where R is in R. And with addition and multiplication, define the usual way. R1 plus I, the sum of two cosets is the sum of their representatives. R1 plus R2 plus I. And the product of two cosets is again the product of their representatives. Is represented by the product of their representatives. And both of these are well defined and make R mod I also into a commutative ring with unit. Further, there is a ring homomorphism surjective onto ring homomorphism. Usually it's denoted by pi or p, pi, going from R to R mod I. And what is that ring homomorphism? It's the one that takes pi of R is R bar. See, R bar, whenever I'm using R bar, it's always notation for R plus I, R bar. The reason for using R bar is that when you use R bar, many things to write down will appear simple. For example, R bar plus S bar equals R plus S bar. This equation is the same as this equation, which says R1 plus I plus R2 plus I is R1 plus R2 plus I. This and this are the same equation. Similarly, R bar S bar equals RS bar. And this equation and this equation say the same thing, right? So these are just alternative ways. If you write it as in terms of bar notation, many things will be easier, but you must always be careful. Remember that R1 bar equals R2 bar does not mean R1 equals R2. It just means R1 minus R2 belongs to I. So all of this bar notation is in the context of one ring R and one ideal I, right? You fix this ring R and fix the ideal I. So when I say R1 bar equals R2 bar, I don't mean that R1 equals R2. It just means that the difference is in I. So the coset of R1 and the coset of R2 are the same. So R bar is just a different notation for the coset of R. So these two mean the same thing. So I will often use this bar notation. Okay. So there is a surjective ring homomorphism from R to R mod I, usually denoted by pi. And one important thing is the relationship between the ideals in R and the ideals in R mod I. So there is a proposition. So this proposition says the following. There is a bijective correspondence, that means 1-to-1 and onto, between the ideals of R that contain I and ideals of R mod I. So that is what this proposition, okay, I'll tell you a little more about this bijective correspondence, but what this proposition is saying is that if you have an ideal of R that contains I, it uniquely corresponds to an ideal of R mod I. And conversely, if you have an ideal of R mod I, there is a unique ideal of R which corresponds to it. Corresponds exactly how? So the correspondence is given as follows. So that's the extra. So the correspondence is given as follows. So I have to give you in both directions, right? If I give you an ideal of R which contains I, what is the ideal of R mod I to which it corresponds? And if I give you an ideal of R mod I, which ideal of R does it correspond? So I will give you in two directions. So if J is an ideal of R, that contains I, then pi j. What does pi j mean? Pi j just means all the cosets R plus I such that R is in J. Right? You take all the cosets of elements of J, that gives you, then pi j is an ideal of R mod I. Sometimes R mod I is itself denoted by R bar. Right? The whole ring bar means R mod, the quotient ring R mod I. So this is in one direction. Conversely, if we take an ideal K in R mod I, so K is an ideal of R mod I. That means it consists of various cosets. Then pi inverse K, by which we mean the set of all R in R such that R plus I is in K. This is an ideal of R. So the statements that I'm making here are very easy to verify and you should verify them. So what should you verify, for example? So I said if J is an ideal of R, then pi j is an ideal of R bar, R mod I. So you have to verify that pi j is closed under addition and pi j is closed under multiplication by elements of R mod I. And similarly, I said if K is an ideal of R mod I, then pi inverse K is an ideal of R. So you have to verify that pi inverse K is closed under addition and that pi inverse K is closed under multiplication by elements of R. So these are just very simple statements. They're saying simple things and you can check. What is not completely obvious is that this is a one-to-one correspondence, right? So I'm saying that this is a one-to-one correspondence. So you need to check carefully that this is actually a bijection between the set of ideals of R containing I. This is a set, and the set of ideals of R mod I. The reason I'm saying you have to check this carefully is there is a reason for saying ideals of R containing I. You will use this in the proof at some point. So in trying to show that this is a bijection, you will use at some point in the proof that the ideal of R that you're starting with contains I. Otherwise, in fact, otherwise you see. So let me try to say. So note, even if J is an ideal of R not containing I, then pi j is an ideal of R mod I. One can check this. So even if J doesn't contain I, pi j is an ideal of R mod I. But this will not correspond in the sense that when you come back using pi inverse, you won't get back J. That's the thing. The only ideals that you will get back from ideals of R mod I will all contain I. Okay, so this needs a little bit of, you must think about this carefully and check that this is a bijection. So you must prove that these two mappings that I have defined are one-to-one and onto and inverse of each other, right? If you show that they are inverse of each other, of course they are one-to-one and onto. So this is a very, very basic thing about ideals of R and R mod I, and we will use this a lot in commutative algebra. This sort of thinking, whenever we think of ideals of R mod I, we will always think of ideals of R containing I. They are essentially the same. They're not the same thing, but they are essentially in one-to-one correspondence. So we will always think of ideals of R mod I as somehow equivalent to ideals of R which contain I. So let us try to apply this, for example, to the rings that we know. So for example, so we know ideals in Z. We know that the ideals in Z are, there is first the zero ideal, and there is the ideal NZ for every n. Zero is also a particular case of this. So the ideals in Z are all the nz's for n in Z, 1z, 2z, 3z, or minus 1z. Note that minus 1z and the ideal minus 1z and the ideal 1z are the same, right? Or minus 2z and 2z are the same, right? The generator 2 and the generator minus 2 give you the same ideal of Z. Okay, we know that these are all the ideals in Z. So let us take a quotient of Z by some ideal. So now consider Z mod dz. Right? So this is a quotient of Z. Quotient ring. So we can ask, in this ring, what are the ideals? So what are the ideals of a quotient ring? The ideals of a quotient ring correspond to ideals of the original ring containing whatever you're quotienting by. So this is my I here. So the ideals here correspond to ideals of Z containing dz. Now let us try and understand what are the ideals of Z which contain dz. So any ideal of Z is an nz. So when does nz contain dz? So we want to understand, when does nz contain dz? So I claim that nz contains dz if and only if. So first of all, if it contains dz, if nz contains dz, the number d certainly belongs to dz, right? So d should belong to nz. Then d belongs to nz, which means n divides d. Nz consists of all multiples of n. If D belongs to Nz, so n divides D. And one can check conversely, if n divides D, then you can check that dz, every multiple of D is also a multiple of n. That's all I'm saying, right? So the ideals of Z which contain dz are exactly correspond to all the divisors of D. So the ideals of Z containing dz are all the nz's where n is a divisor of D. I should have called it D. I meant to do the other way. I wanted to call n as D and D as n, but I did it opposite. Anyway, it doesn't matter. Fine. So all the n's where n divides D. So if you want, so the ideals of Z mod 12Z. If you want to know what are the ideals of Z mod 12Z, they correspond to all the ideals of Z which contain 12Z, which means all divisors of 12. So divisors of 12. 1, 2, 3, 4, 6, and 12, right? That's all, no? So these are the divisors of 12. So what are the ideals of Z mod 12Z? So the ideals here are pi of 1Z, pi of 2Z, up to pi of 12Z, where pi is the map from Z to Z mod 12Z, which takes pi of some k is just k plus 12Z. That's k bar. So the ideals here, how many ideals are there? 1, 2, 3, 4, 5, 6 ideals. No, there are exactly 6 ideals in this ring. There are only 6 ideals in this ring, and the 6 ideals are the images of 1Z, 2Z, and so on up to 12Z. Right. So this gives you a way of seeing what the ideals in quotient rings are, and this is important to know. It's important to know this thing. Okay. Fine. The next thing I'd like to do is, so I want to define, so in ATM McDonald, there is a whole discussion of what kind of elements are in rings, right? There's a classification of elements that belong to rings. So there are, I want to make some 5 definitions, right? So types of elements in a ring. So what I would like to do is to make 5 definitions. I'll make 5 definitions, then we will discuss various examples of these. So first, so R is a ring. As usual, ring means commutative ring with 1. Okay. So that's all I'm assuming about R. I'm not assuming anything else. Just it's a ring, that's all. So there are various types of elements. U in R is said to be a unit if it has a multiplicative inverse in R. The important thing is multiplicative inverse in R, i.e., if there exists V in R such that UV equals 1. So this is the first kind of element. Units. The units of a ring play an important role, particularly if in number theoretic rings, like, you know, I gave you examples of Zi and Z omega. Knowing what the units of a ring are is often useful. So let's try and see in the rings that we have, what are the units in the rings that we have defined. So first, let's see in Z. In Z, What are the elements of Z which have a multiplicative inverse in Z itself? See, 2. Of course, 2 has a multiplicative inverse half, but half doesn't lie in Z. So 2 is not a unit of Z, right? The only elements of Z whose inverses are also in Z are plus and minus 1. So plus minus 1 form the units of Z. Okay, let's see what it is in Kx. You're looking at polynomial rings. I want to know if I have a polynomial fx, when can I find a polynomial gx such that the product is 1? But the degree of a polynomial, degree of a product is the sum of the degrees. So if the product has to be 1, then your original polynomial had better be of degree 0. That means it must be an element of k. And if it must have an inverse, it has to be a non-zero element of k. So the units here are k star. The non-zero elements of k are the units. Similarly, if you do kxy, then again you have a polynomial in 2 variables. When is its inverse? There is one by that polynomial. Also a polynomial, the only case is when that polynomial had better be of degree 0, it should not involve x and y, and it should be in k star. So here also it is k star. See, when you get to z adjoint I, interesting things happen. What are the units of z adjoint I? So first, what are the elements of z adjoint I? So the elements are a plus bi, where a and b are in z. So we want to know which of these elements can you multiply by another c plus di and get 1. So I want 1 over a plus bi to also be of the form a plus bi, where those two things belong to z, right? So this needs a little bit of a trick. So in zi, there is a norm function defined. I'll define the norm of a plus bi to be a squared plus b squared. Okay, let me define the norm of a plus bi to be a squared plus b squared. So the norm is now a function from zi to z. N is a function from zi to z. And the most important property of this norm function is that it is multiplicative. So proposition, very simple and important proposition. So the norm is multiplicative. I.e., norm of zw equals norm z, norm w. For z and w, of course, in zi, the norm is defined on zi. And this, so this is just a calculation. So
the GCD should be 1, right?
GCD of what?
Z and W.
No. Z and W. No. Z and W are elements of Zi. They are of the form a plus bi.
Yeah. So it's an integral domain. So we can talk about GCD of any two.
We can talk about GCD. That is correct. We can talk about GCD, but this has nothing to do with GCD. This is true in general.
Okay.
The norm is always multiplicative. So I will prove it for you, right? So suppose Z is a plus.
The definition of, so usually the stated definition for multiplicative, the GCD of 2 elements should be 1. That's it.
No. Oh, okay. You're confusing with another. Okay, that definition in number theory, there's something called a multiplicative function.
Okay. Yeah.
Okay, I'm not. This is not that. This is not that definition. This is not defined on integers. This is defined on the ring Zi. Multiplicative just means that n of zw equals nz nw. Now, without any restriction on GCD, nothing. Okay, that definition of multiplicative is for a multiplicative function on the natural numbers. Don't confuse with that. It's a different definition. Although the same term is used, it's a completely different definition. Right? By multiplicative, I just mean this property. That's all I mean. Nothing to do with GCDs. Okay? So suppose Z is A plus BI and W is C plus DI. So what is the norm of Z? I've defined it as A squared plus B squared. And what is the norm of W? Similarly, it is C squared plus D squared. These are elements of Z, right? Now, what is ZW? So ZW is the product A plus BI into C plus DI. So we calculate. So we know that this is AC minus BD plus AD plus BCI. This is how you multiply complex numbers. So this is the answer. So what is the norm of ZW? Norm of ZW therefore is AC minus BD whole squared plus AD plus BC whole squared. And this you can calculate. So let's calculate. A squared C squared plus B squared D squared minus 2 AC BD. That's for the first term. Plus A squared D squared plus B squared C squared plus 2 AD BC. Now you notice that this ACBD and ADBC, these two terms cancel. So what are you left with? So you're just left with these four terms, and these four is the same as A squared plus B squared into C squared plus D squared, which is norm Z times norm W. This is an important property of the norms defined on the ring Zi. So by the way, the ring Zi is called the ring of Gaussian integers. So why am I doing this? Our goal is to be able to determine what are the units in this ring. I want to know what are the units in Zi. So suppose that U in Zi is a unit. What does that mean? Then there exists a V in Zi such that UV is equal to 1. And now we use whatever we know. We know that the norm is multiplicative. So let us calculate the norm of UV and compare it. So norm of UV equals norm of 1. 1 means what? 1 plus 0i. And the norm of 1 plus 0i is 1 squared plus 0 squared. That's just 1. So the norm of UV must be equal to 1. But norm is multiplicative. So this is equal to norm of U times norm of V. So the product of these two things is 1. But where do norm U and norm V lie? Norm U is something squared plus something squared. And norm V is also something squared plus something squared. So these are both positive integers. So since norm U and norm V are both positive integers, both must be 1. If the product of two positive integers is 1, then both must be 1. Both must be 1. So norm U equals 1. So if U is some A plus BI, then A squared plus B squared must be 1. A and B are integers, and A squared plus B squared equals 1. What can they be? One has to be 1 or minus 1, and the other has to be 0. So one of them is plus or minus 1, and the other is 0. So this gives 4 possibilities. And what are the 4 possibilities? If A is 1 and B is 0, that gives 1. If A is minus 1 and B is 0, it gives minus 1. If A is 0 and B is 1, it gives I. And if A is 0 and B is minus 1, it gives minus I. And so if U is a unit, it has to be only one of these. That's all we have shown. So far we have shown that if U is a unit, then u must be equal to either 1, -1, I, or -y. And these are all units, easy to check. These are all clearly units. Why are they units? The inverse of 1 is itself, the inverse of -1 is itself, the inverse of I is -I, and the inverse of -I is I. That is I times -I equals +1. And so all of these are units. So the units of Zi are these 4 elements. So this is somewhat more interesting than the previous cases, which were very simple. Similarly, there is a calculation for the units of ZW. Okay, I don't want to get into that. I'll just say similarly, it is possible to calculate all the units in the ring Z omega. Omega is a cube root of unity. Okay, but let me not get into that. So all I'm trying to point out is, so far what I'm trying to point out is it is important to know what units are in a ring. Unit means something which has a multiplicative inverse in that ring, right? You should not get confused. For example, 3 is not a unit in Z, although 3 has a multiplicative inverse. In Q, 3 has a multiplicative inverse in Q, which is a larger ring. 3 does not have a multiplicative inverse in Z. So 3 is not a unit of Z. But 3 is a unit of the ring Q, right? So whether it is a unit or not depends on which ring you are considering. The same number may be an element of several rings, and it may be a unit in some of them, it may not be a unit in others. It depends both on the element and on the ring in which you are considering. So this is the first definition, unit.
Professor, I have a doubt.
Yes.
Professor, you told me that the units of Zi are, there are 4 units are there as far as Zi is concerned.
Yes.
Can we view these units as the units of Z cross Z also? Zi can also be viewed as Z cross Z. Can I do like?
Yes. Okay. There is a slight problem with that. So let me explain. Yeah, Zi is in some ways it is the same as Z cross Z. In some ways it's different. So I think it's a good point. Let me just address this issue. Okay.
The doubt is that if it is the case, can it be generalized for Z?
No, it is not the case. But the thing is, it is not the case. Okay. So there is no question of generalization. These are not Zi and Z cross Z are 2 different rings. So let me just explain that. So recall that if R1 and R2 are rings, then R1 cross R2 is also a ring. With what operations? With component-wise operations. We know this. So therefore Z cross Z is a ring. And what are its elements? With elements A comma B, where A and B are in Z. Now you might be tempted to think of this as Zi. Now Zi also looks like A plus Bi. Essentially it is one A and a B, right? But these 2 rings are definitely not the same ring. The ring Z cross Z and the ring Zi are very different rings. They are not isomorphic rings. However, Zi is not, this is not an integral domain, exactly. Zi and Z cross Z are not the same ring, are not even isomorphic rings. Are not isomorphic rings. See, if you want to show 2 rings are isomorphic, then you can construct. You can try to construct an isomorphism between them. But if you want to show that 2 rings are not isomorphic, how do you do such a problem? You usually do that by finding a property that one satisfies that the other does not satisfy. So in this case, being an integral domain is such a thing. So I'm coming to integral domains soon. Anyway, I've mentioned them several times already. Formally, I'll do them. I'm sure all of you know what an integral domain is already. Notice that Zi is an integral domain. So why is Zi an integral domain? Zi is contained in, say, complex numbers. Complex numbers form a field, right? So fields are integral domains. Subrings of integral domains are integral domains. So Zi is certainly an integral domain. But Z cross Z is not an integral domain, because if you take the element 1, 0 times 0, 1 in Z cross Z, you have to multiply component wise. So 1 times 0, 0 and 0 times 1, 0, right, in Z cross Z. So here you have two elements in Z cross Z whose product is 0, but neither of these two elements is 0. So Z cross Z is not an integral domain. So this is not. Okay? I'll just say domain. But Zi is. So these are very different things. So you cannot think of Zi as Z cross Z. Ring-wise. Ring-wise, you cannot think of it as Z cross Z. It is the same as Z cross Z as abelian groups, for example. But it is not the same as Z cross Z as rings. They are two different things. Okay. Fine. So that's the first type of element, units. So the second type of element I want to define is something called a non-zero divisor. So A in R is said to be a non-zero divisor if okay, let me, I would rather define zero divisor. So A in R is said to be a zero divisor if there exists a B in R, B not equal to 0, such that AB is 0. Let's try to understand this definition. So I'm trying to define, zero. I'm trying to define something known as a zero divisor. A zero divisor in a ring is an element such that for some other element which is not 0, you multiply with A and you multiply with this and then get 0. If there exists such a B which is not 0, such that AB is 0, then we say that A is a zero divisor. For example, 0 is a zero divisor in any ring. Any ring R, not the zero ring. I told you that there is one ring, one very special ring called the zero ring, which has only one element, 0, and that is also the multiplicative identity, that's also the additive identity. It has only one element. That is a ring that's also regarded as a commutative ring with identity, but it's a somewhat special case, right? So I claim that if you take 0 in any other ring, then it's always a zero divisor, because 0 times 1 will be 0, but 1 is not 0, right? If in a ring which is not 0, 1 is not equal to 0. Fine. And in Z, and we already just saw that example, in Z cross Z, the element 1, 0 is a zero divisor. 0, 1 is a zero divisor. Element which is not a zero divisor, it's said to be a non-zero divisor. So an element of R which is not a zero divisor is called a non-zero divisor. This is what is usually used, NZD. Non-zero divisor means it is not a zero divisor. That means if you multiply it with any element which is not 0, you will end up with an answer also that is not 0. Right? So with this, with the definition of zero divisors, we can define, so integral domain, which everybody knows. So R is said to be a domain or integral domain, which I'll just say domain, if there is no zero divisor in R except for 0. 0 always is a zero divisor, but if everything else is a non-zero divisor, that means you cannot multiply two non-zero elements of R and get 0. That's the usual definition of an integral domain, is a ring without zero divisors. And most of the examples of rings that I have given, I mean, the main examples of rings, the 5 examples that we have considered, are all integral domains, right? Where are they? Oh. Wait a second. So all these examples of rings, fields, Z, Kx, Kxy, Zi, Z omega, all of these are examples of integral domains. You cannot multiply two non-zero elements and get 0. So if all of these are examples of integral domains, why are we ever considering other kinds of things? The reason we are considering other kinds of rings is these are not the only examples. As I said, to get lots of examples of rings, you begin with these and then take quotients by ideals. If you take the quotient of a ring by an ideal, then you get a quotient ring, and that quotient ring may no longer be an integral domain. So let's get to that. So, for example, let's take our favorite Z mod 12Z is not an integral domain. So we know what are the elements of Z mod 12Z. The elements of Z mod 12Z are, we know, 0 bar, 1 bar, 2 bar, up to 11 bar. And 2 bar means the coset 2 plus 12Z. 11 bar means the coset 11 plus 12Z. Okay, so these are the elements of Z mod 12Z. These are all the 12 distinct elements of Z mod 12Z. And notice that 3 bar times 4 bar is 12 bar. And 12 bar is the same as 0 bar because 12 belongs to 12Z. So 3 bar times 4 bar is 0 bar. But 3 bar is not 0. And 4 bar is also not 0. Right? So this is not a domain. And quotients of Z mod 12Z is quotients of Z. It's very easy to decide when it is a domain and when it is not. So we know, for example, for Z, we know that Z mod dz is a domain if and only if D is either 0 or a prime. So if it's a prime, I claim that Z mod dz is a domain. And if it is not a prime, then it's not a domain, except 0, of course, right? 0 is not considered a prime. But Z mod 0Z is just Z. And we know Z itself is an integral domain. And Z mod primes, I claim, are integral domains. But Z mod non-primes are not integral domains. So let's just see this. It's easy to see. So if D is not a prime, so write D equals AB, where neither A nor B is 1. I'm assuming that D is a positive integer, right? Prime means it's not a product of smaller integers, not involving 1, right? So write D as AB. Then in Z mod dz, A bar B bar equals D bar, which is 0 bar, but A bar is not 0 because D doesn't divide A, and B bar is also not 0. So that means this is not an integral domain. So Z mod dz is not an integral domain for D not a prime. What about Z mod dz when D is a prime? So what about Z mod pz? We know, in fact, this is a field, right? We know that Z mod pz is a finite field. So of course it's an integral domain, but how do you actually see it? So Z mod pz, if A bar, B bar belong to Z mod pz, are both non-zero, are both not zero bar. That means what? P doesn't divide A and P doesn't divide B. Then of course, by the way primes work in Z, so P doesn't divide AB, which implies A bar, B bar is not zero bar. So the product of two non-zeros is still non-zero. That means Z mod pz is an integral domain. Okay, so this is the second definition, zero divisors and integral domains. Third definition is that of a, this may be not as, one second.
Nilpotent.
I said I had 5 things. Okay, yeah. Okay. So the third thing I want to do is nilpotent. So an element in a ring is said to be nilpotent if some power of it is 0. So A in R is nilpotent if A power n is 0 for some natural number n. Either A is 0 or A squared is 0 or A cubed is 0, some power of A, some positive power of A. If it is 0, then we say it's a nilpotent element. Now, in the usual rings that we deal with, like Qx and Z and all, there are no nilpotents. In an integral domain, you cannot have a nilpotent. So if R is a domain, no element other than 0 is nilpotent. That's not very interesting. You cannot have a power of A to be 0. If A is not 0, then A power n is also not 0, because when you multiply two non-zero elements, you always get a non-zero element. So in a domain, no element other than 0 is nilpotent. So once again, we might ask, why should we study nilpotent elements? They are fairly rare. But they are only fairly rare because the rings that we were looking at are all integral domains. Once you go to quotient rings, there are plenty of nilpotents will happen. So here's an example. Again, let's do our favorite example in Z mod 12Z. Is there a nilpotent? Non-zero nilpotent. Of course, 0 is always nilpotent. Is there a non-zero nilpotent element? So Z mod 12Z, as I said, is just 0 bar, 1 bar, 2 bar, 3 bar. This is Z mod 12Z. So is any element of these nilpotent? That means I want to take an element and take powers. And after taking powers, it should become 0. After taking powers, it should become 0. So notice that if I take 6 bar squared. What is 6 bar squared? 6 bar squared is 36 bar. And 36 bar is 0 because 12 divides 36. So 6 bar is nilpotent. Is anything else nilpotent? In this ring, can any other number be nilpotent?
3 bar.
Pardon?
3 bar, 4 bar, 2 bar.
No, 3 bar. No, wait. 3 bar I claim is not nilpotent. Okay. If you take the powers of 3, what will you get? You will get 3, 9, 27, 81, all odd numbers, right? None of them will be divisible by 12. So if you take 3 bar to any power, you will never get something which is 0 mod 12, something which is divisible by 12. So 3 bar is not nilpotent. Similarly, 4 bar is also not nilpotent. If you take the powers of 4, you will never get a multiple of 12, right? Because 3, somewhere 3 has to come. So if it has to be divisible by both 3 and 2 at least, right? Because when you take, so the only nilpotent here is 6 bar other than 0. So the nilpotents in this ring form the set 0 bar 6 bar. So the set of nilpotents here is 0 bar 6 bar. Notice that this is actually an ideal. Note that this is an ideal in Z mod 12Z. It's closed under addition, it's closed under multiplication by any element of that thing, right? This is actually a ideal in Z mod 12Z. Okay.
So in the finite ring, the nilpotency always less than or equal to the cardinality.
Pardon?
In a finite ring, the nilpotency of the element should be less than the cardinality of the ring. Is always maybe more.
Yeah, that is likely because there is that is likely. Yes, that's true. Yes, that's correct. Yes, that is correct. Yes, in finite rings. But our interest is not really in quotients of Z. Okay, our interest is in more the whole field of commutative algebra is to study these concepts in as much generality as possible. Although the examples I'm doing are these small examples, the real things are where you have, for example, quotient of kx. So let me take this example. So let me take kxy mod the ideal generated by x squared, xy, and y squared. This is a monomial ideal. This is an ideal generated by monomials. So these are interesting examples of rings. You take kxy and take a quotient by a monomial ideal. So these kind of rings are not very well behaved in various ways, but they are well behaved in various other ways. But anyway, so these are examples of rings. So for example, here in this, are there nilpotent elements in this ring?
X and Y.
X is nilpotent. So x bar squared is x squared bar, which is 0. So x is nilpotent. So x bar is nilpotent. And x bar is not 0, by the way. We are always interested in non-zero nilpotent. 0 is always nilpotent, right? X squared also is nilpotent, but x squared is 0 in this ring. So x bar is not 0 because x doesn't belong to this ideal. The ideal generated by x squared, xy, and y squared does not contain x. X you cannot write as a combination of degree 2 polynomials, right? So we have a non-zero nilpotent. Similarly, y bar is also nilpotent.
Xy also.
Xy is 0. That's what I was trying to say, right? Xy is 0 in this ring. I'm not interested in 0. I'm interested in non-zero nilpotents.
Okay.
Right? Y is also nilpotent. Y bar is also nilpotent and non-zero.
So the sum x plus y.
Right. Sum x plus y. So what about x bar plus y bar?
Square if you take square.
Yeah, is also nilpotent because if you square it, x bar plus y bar square is x bar squared plus 2x bar y bar plus y bar squared. We know all of these terms are 0. X squared is 0, 2xy is 0, y squared is 0. All of them belong to that ideal, right? So x bar plus y bar squared is also 0 bar. So x bar plus y bar is also nilpotent. In general, we will see that the sum of nilpotent elements is also nilpotent, and that's the reason why the nilpotents form an ideal. I'll get to that soon. Okay, so nilpotent. Yeah, so one more type of element that I would like to define is something called an irreducible element. So I said 5 types of element, maybe only 4 types I have.
Idempotent elements.
Yeah, idempotence, I'm not going to go into idempotence right now. So the next type of elements is irreducible elements. So it's useful to define irreducible elements when the ring R is a domain. So I will start with let R be an integral domain. So unlike all the others which were defined everywhere, these irreducibles are usually defined in integral domains. So let R be an integral domain. So we say that an element A in R is irreducible. First, it should satisfy some condition. If it is not 0 first, not a unit also, it should not be invertible at that time. So it's not 0, not unit. And whenever A equals BC with B and C in R, then either B or C must be a unit. So an irreducible element is something which cannot be written as a product of two things. Everything can be written as a product of a unit one times itself, for example. Or for example, it need not be one times, it could be a unit times some other thing. That's always possible. But things which cannot be written as a product of two non-units, B and C both being non-unit, those are called irreducible elements in an integral domain. So we know lots of examples of irreducible elements. In the familiar rings such as Z and Kx, we know lots of examples of irreducible elements. So let's just look at this a little bit. So in Z, any prime is irreducible. So 7 or 3 or 13, all of these are irreducible in Z. They cannot be written as a product of two things, with both of those things being non-units. Similarly, in Kx, polynomials such as x minus alpha for alpha and k are irreducible.
Any second degree polynomial.
Any? Sorry,
second
what
degree polynomial, any second degree polynomial, but does not have a root.
Any second degree polynomial?
It does not have a root in K.
That does not have a root. Yes, those are also irreducible. I'm coming to that. So all these linear polynomials are irreducible because just by degree, if you can write it as a product of two other polynomials, right? Since the degree is 1, since the degree of this is 1, one of those two must have degree 0. That means it must be a unit. That means it must belong to K, right? So that shows that linears are irreducible. Further, quadratics without roots are also irreducible. So if you take some ax squared plus bx plus c, why is it irreducible if it doesn't have a root? If it reduces, then it's the product of two polynomials. Both of them have to be of degree 1 because we have said that neither of them should be a unit. Then both of them must be of degree 1. So if it reduces, then it's of the form some px plus q times rx plus s, which will imply that minus q by p will be a root. If it reduces, it will have a root. So if you have a quadratic without a root, then that will be irreducible. So in Rx, x squared plus 1 is irreducible. Or in fact, x squared plus any positive number, x squared plus 3, etc. Any quadratic without a root will be irreducible in Rx. And in fact, the only irreducibles of Rx are the quadratics without roots and the so let me state that. So this is a theorem. not extremely easy. The only irreducible polynomials in Rx are the linear polynomials and the quadratic polynomials without a root. This statement is equivalent to the statement that the field of complex numbers is algebraically closed. It follows from that, and if you know this, it's equivalent. Both these statements that the C is algebraically closed and this are equivalent. Anyway, let's not get into this. So anyway, we have the concept of irreducible. So what I would like to say about irreducibles are, I want to make two comments about irreducibles. What is the relation between irreducibles and primes? So relation, oh, I did not define what's a prime element, no, so far. So that's the fifth one. So the fifth type of element is a prime element. Again, prime elements are defined in integral domains. So they can be defined in general, but we will use them mostly for integral domains. So I'll just define it in an integral domain. So let R be an integral domain. P in R is said to be a prime if whenever P divides BC for B and C in R. Either P divides B or P divides C. Again, we know examples of primes. In Z, for example, the usual primes are primes. In Z, usual primes are primes. But also, according to this definition, -3 is a prime. Prime element of Z. If -3 divides the product of two elements, then easy to see that -3 has to divide one or the other, using the fact that 3 is a prime of regular usual prime, right? So, so in Z, the usual primes are primes. In Kx, we see that Kx. So elements such as, again, I'll give x minus alpha. Prime. Let's try to understand this. Why is x minus alpha a prime element of Kx? So what I'm trying to say is, if x minus alpha divides a product of two polynomials, then either x minus alpha divides one or x minus alpha divides the other. So let's just see this. So suppose x minus alpha divides fxgx. So we want to show that x minus alpha divides fx or x minus alpha divides gx. But what does it mean to say x minus alpha divides fxgx? Fxgx equals x minus alpha times some other polynomial qx. We know this given. Just set x equal to alpha. So there is a homomorphism from kx to k by setting x equal to alpha. So set x equal to alpha to get f alpha g alpha is 0. But f alpha and g alpha are elements of k. And k is definitely an integral domain. It's a field. So if the product is 0, f alpha is 0 or g alpha is 0. The product of one, the value of one at alpha or the value of the other at alpha is definitely 0. What does it mean to say f alpha is 0? Now we use the Euclidean algorithm or the remainder theorem. Use Euclidean algorithm. Write fx as x minus alpha times some rx or tx plus some number beta. But f alpha is 0, which implies beta is 0. Just substituting alpha here, this will become 0, that will become 0 at alpha, and therefore beta must be 0, which means that x minus alpha divides f of x. Right? So elements like x minus alpha are prime elements in the polynomial ring Kx. And the question of what are the primes in Zi is a much more interesting and delicate question. So this has a very interesting answer. So I'll try to discuss this next time if needed. Let me see. So okay, I won't say anything more about this right now. So what I would like to see is, so we have defined two notions which look very similar. In Z, irreducible elements are also the prime numbers. Prime elements are also the prime numbers, basically. So what is the relation between irreducibles and primes? So this is what I would like to address. So relationship between irreducible elements and prime elements in a domain R. Take a domain, integral domain R. I want to know what is the connection between the irreducible elements of R and the prime elements of R. Okay, and for this, so let's notice the following.
In PID both are equal.
Pardon?
In the principal ideal domain, everything is equal.
The principal ideal?
In the principal ideal domain, both the things are equal, both the concepts.
Yes, in a PID both are equal. I'm coming to that. Yes, I'm coming to that. So, but before that, before getting into PIDs, let me observe one thing. So here is a lemma. In any integral domain, prime elements are always irreducible. Always. This has nothing to do with PID or anything. You just take any integral domain, prime elements are always irreducible. So let's prove this. It's easy proof. So say P is in R and P is prime. Oh, so one second. So let me just go back slightly and see what is the definition. So I said P in R is said to be a prime if whenever something happens. Again, I should say P is non-zero, non-unit. I should have said that if P not equal to 0, P not unit. Both primes and irreducible elements should be non-zero, non-unit, right? They should not be 0 and they should not be units, and then this property, right? Okay. So let P be in R and P is a prime. So we want to show that P is irreducible. So suppose it's not, or let me say, suppose P can be written as BC, where B and C belong to R. You know that P is a prime. What does P is a prime mean? P is a prime means whenever P can be written as BC, whenever P divides BC, P divides B or P divides C. But P is prime. And P divides BC because P is equal to BC. This implies P divides B or P divides C. So say P divides B. What does P divides B means? That means B equals P times some S for some S in R. And this equation I will substitute into this equation. Hence P equals PSC, which implies P into 1 minus SC is 0. But you are in an integral domain and P is non-zero and non-unit. So P is not 0. Not 0 means the other term must be 0. So 1 minus SC equals 0 since R is a domain. But this means what? That means C is a unit. Because C times something is 1. So C is a unit. So we have shown that if you write it as a product, right, then P has to divide one of them. The other one will be a unit. If P divides B, then C is a unit. If P divides C, then B is a unit. So in any case, one of them will always be a unit. So either B or C must be a unit, which implies P is irreducible. That's the definition of irreducible. An irreducible element is one which, when you write it as a product of two elements, one or the other must be a unit. So this is a very, very general thing. In any integral domain R, prime elements are always irreducible. Now the converse is not true. Okay. So this is a fact. That is, there are integral domains and there are irreducible elements in that integral domains which are not prime. So I want to give you an example. This is a rather, how do I say? It might look like a contrived example, but this happens quite often. So here's an example. So let R be Z adjoint square root minus 5.
Take 6.
Yeah. So the element 6 will have, okay. So I want to give you an example of something which is irreducible but not a prime. So in R, the element 2 we can show is irreducible, but not prime. So we can show how. How can we show that 2 is irreducible but not a prime? So if you want to show that something is irreducible but not a prime, so you have to show it's irreducible first, then you have to show it's not a prime. So, okay, it's a rather long proof. I don't want to go through this. So okay, let me just say. So we can show that 2 is irreducible using that norm function. N of A plus B root minus 5, J squared plus 5B squared. One can show that this is a norm function, this is multiplicative, all the usual things, right? Like I did for Z adjoint I, you can show that this is multiplicative, and using the norm function, we can show that 2 is irreducible. And how do you show 2 is not prime? To show that 2 is not, I'm not giving the full proof, I'm just sketching. To show that 2 is not prime, notice that 6 can be written as 2 times 3, can also be written as 1 plus root minus 5 into 1 minus root minus 5. So 2 divides 1 plus root minus 5 into 1 minus root minus 5 in this range. Because 2 divides 6, it's 2 times 3. However, 2 does not divide 1 plus root minus 5. 1 plus root minus 5 cannot be written as 2 times some element of this ring, and 2 does not divide 1 minus root minus 5 either. And so it is, therefore, it's not a prime, but it is irreducible. It is irreducible, needs a proof. I only sketched the proof, right? So here, so it's not true that irreducibles are prime. It's only true that primes are always irreducible, but irreducibles need not be prime. There is an important case in which irreducibles are prime, and this is the proposition. If R is the principal ideal domain, and what does this mean? That is a domain where every ideal is principal, where every ideal is generated by a single element. Then in R, irreducibles are prime. So since time is over, I will stop now. We will start with this next time. So we'll start with this thing next time. Are there any questions?
So how to define the norm of any general ring, if it is set of omega or something, is set of something? How to guess that function norm?
The function norm, okay. This function norm is actually coming from some number theory, and these rings are rather special kinds of rings where there is a norm function defined. In general, there is a norm for any field extension, and it's a specialization of that thing. These are all specializations of that norm defined for any finite extension of fields.
Okay, then any norm gives the same number of units. Same units.
No, the units have nothing to do with the norm. The norm is something extra. The units depend only on that ring itself, right? Once you have a ring, you know what a unit is in that ring. It has nothing to do. This norm is something extra that you are defining to do the proofs. The norm on this ring is not part of that ring, right? It's something extra that you're defining.
We derived the ring units using this norm function. That's why I'm asking that.
I did not understand. Can you just repeat?
So in the set of I, we derived that the units are plus or minus 1 plus or minus using the norm function.
Yes.
So if you suppose if you sum other norm function, you'll get the same units.
Yes, because that's what I'm trying to say. The units are dependent only on the ring. The definition of a unit depends only on that ring R. The norm was only one device that we used to prove that statement. So the units of that ring are this much. We have proved it. So whichever way you do it, you have to get only that same answer, because they are the units. The unit doesn't depend. The definition of unit did not depend on norm or anything, right? It was only related to that ring itself. The norm was only some technical device we used. Any other questions? Okay. So then we will stop here and continue on Thursday. Thank you.
Thank you, sir.
Thank you. Thank you, Vijay, sir. So participants, you please note tomorrow's session will begin at 5:15, and the session is about linear algebra by Professor Raghavan sir. Thank you. Thank you one and all. Thank you, Vijay sir.